Okay, so for today, we are going to continue. We're not going to really cover anything that we haven't seen already, but today we're going to combine what we know about quadraphonic sound with what we know about patterns. So we've used patterns in a stereo context, and we've started to make some quadraphonic sound using unit generators. But we haven't yet combined patterns with quadraphonic sound. All right, so our sounds for today, I have these trombone tongue pops, and I think these will play. Yeah. Right. So some weird trombone extended technique stuff. Because we're going to be working with patterns, I think it's good to it's instructive, clear to use nice and short sounds. So that'll be sort of the focus today. So let's crack open SuperCollider here and get things started with our usual. Now I noticed that I guess somebody changed the settings so when you open up a bracket, it automatically makes the closing bracket, right? Which I guess I probably should have been doing that all along because that's actually pretty handy. Yeah, well, thank you. Might take me a little getting used to, but I think that's going to ultimately be faster. All right. So number of output bus channels. Oh, we'll just go with the full 10. Rec channels, and of course the first two are dummy channels, and we're doing quadraphonic sounds. So the minimum here we need is 6, and we should be able to just boot the server like that. And we've got the Motu over here, and I think I'm just gonna. I'm gonna start by just reading one of these sound files in. So what is it? This process. I've already saved this. Oh no, I didn't. Let's go ahead and save this. Desktop field steel code. We're gonna overwrite that, and so now. This process now exceeding path gives us that. So we're going to say path name. I forget if I mentioned this, but throughout SuperCollider, in almost 95, 99% of the cases where we say object.new, we can often just omit the .new and it will still work. So I'm going to try to do .new for clarity, but like synthdef.new, synth.new, window.new, etc. Those can usually be omitted and it still works. So it's syntactical shortcuts that aren't great for teaching but are very good for coding. Parent path. Try to stay on topic here. Plus, I think it's called source. Slash, we'll use this one here. So that is okay. So this gives us our string. Right? No, I need quotes over here. Oh, see now this double thing is sort of messing with me. I might disable this just so I don't. I'll turn it back on at the end. Behavior. Okay. So that's our string. So we can say and there we go. Let's make sure this is working. Out.ar2. Oh, I think this is a stereo. Yeah, that's a stereo file. So we're going to not just read, but read channels. Read channel, I think it is. So read channel, slightly different method, which allows us to read only a specific number of channels from a multi-channel file. So this gives us a monophonic buffer. We are ready to roll. To get started with patterns and quadraphonic sound, I'm going to make a synth-def. Call it play. What kinds of arguments are we going to need? We'll start with a buffer number. We'll give it an amplitude, a pan position, an output bus. We'll add to those as we need. Let's make a signal and an envelope. Let's add a playback rate. That's always nice to have. Let's add a start position. Default that to the very first frame with index 0. I'm going to let our envelope handle done action 2. We're gonna. I have the mixer configured for circular panning. So the order on the back is what red, orange, green, yellow, in outputs 1, 2, 5, and 6 as it appears on the course website. So pan AZ is we're good to go at it with regard to using pan AZ. So a 4-channel sound, our input signal, our pan position, which is called pan. We'll put our amplitude argument here. Width 2 is fine. I don't really feel like modulating that. And 0.5 because the front of the space is a pair of speakers. Multiply this by our envelope and send it out. I'm going to default out to 2 because we're in Studio X, and that will give us the correct configuration. And now, I already know what I've forgotten. I need attack and release. And let's see if hey, all right, first try. So we're dealing with, the only sound we've loaded into a buffer is this really short trombone tongue pop. And we've got a homemade percussive envelope that we're applying to that sound and then we're panning it in for space in a circular fashion. So remember, a pan position of 0 is the front, pan position of either negative or positive 1 is the back, and as we go around from back to front to back in a clockwise fashion, the pan position goes from -1 up to +1. It's a nice clean way of thinking about it. Of course, this can all be done in Cartesian space using pan 4, but if you want to do circular motion, it becomes a little more cumbersome because you've got to use trigonometry and sine waves out of phase. But we're just gonna, today we're just gonna focus on pan AZ. Let's see, let's just make sure it works real quick. Ugh, this is what I get for typing in 2 different keyboard layouts. Just all sorts of egregious typos. So we'll say buff B amp 0.5 pan minus 0.5, puts it on the right, positive 0.5, sorry, left, positive 0.5 on the right. That's behind me, and so is that. So I think this is working just fine. So when we start to get into patterns, really the first question we want to ask ourselves is, what do we want to do? What kind of spatialization do we want to do? And I was sort of tinkering around before class, and we can start with a sort of obvious idea of using patterns to make a sound go around in a circle, just as a clinical example. Not the most sophisticated or interesting thing, but it's something we can do, and it'll give us an entry point into patterns. So we're patterns, we have a p-bind, which we're going to play. We need to provide the name of the synth-def, a delta time, or a duration time between onsets of successive events, 0.1, so that would give us 10 events per second. Our buffer is going to be B. Sometimes what I do is I will just copy these and then just paste them down here and then format them, just so I don't have to be constantly looking at what I have. But if that's something you want to do, then go for it. Rate is just 1. See, so we've got out 2. Not paying too much attention here, but it's worth mentioning that these can be in any order. It really doesn't matter the order of the parameters in your p-bind, because as p-bind is played and generates events, all these parameters get grouped together in the next event and sent out. So don't worry about order here. So I'm just going to play this, and since we've named it p equals p-bind.play, we'll be able to stop it with p.stop. Turn this up a little bit. I'm going to adjust the envelope settings. We're going to have a very short attack and a release, which is also very short. So really, you can take any sound file, and as long as your envelope is sufficiently short, you get a nice little percussive, thunk of some kind. For variety's sake, let's randomize the start position. Now, for start position, this expects a value in frames, so it starts at 0 and goes to the number of frames in the buffer minus 1. And because we're in a p-bind here, we can just use a language side method like num frames, b.num frames. This will give us the number of frames in the buffer, and we can just subtract 1. So we could do something like this. This would give us the full range of the buffer, but it doesn't really make sense to start at the end, because there will be no audio for the envelope to read, right? We're already at the end of the file. So maybe we can just read from the first 3/4 of the file. So I'm saying how many frames are in this buffer, what's the last frame, or we don't even need that -1 anymore. However many frames are in there, don't choose any value higher than 3/4 of that value. And do that forever. So now each time a p-bind generates an event, it'll start from a random place within the first 3/4 of that file. And if we were to crack open this file here, we can see that it's, if we happen to choose a starting point around here, we'll get a nice big amplitude blump right around there. But if we happen to choose around here or here, it's going to be fairly quiet. So this is an interesting spin on randomizing amplitude. We could just always start at the same start position and just randomize amplitude, but that would sound a little bit different. But this way I think this is kind of interesting. Let's actually limit our selection even more, starting only in the first 1/4 of the file. I just want a little bit of variety in our sounds, so we're not listening to a machine gun. That's just the exact same sound over and over again. And if you like, you can keep going and sort of randomize a little bit amplitude, make the envelope a little bit random, randomize the playback rate. There's lots of interesting nuance, bits of nuance that you can insert. So let's make this go around in a circle, shall we? The pan position is, if it's just 0, it's right in the front. If it's 0.5, it's to the right, and minus 0.5 to the left. Of course, we're inside of a pattern, so we are not limited by using fixed values. We know some of these patterns already. We can say p white, minus 1.0, 1.0, inf. That's very exciting. And all of a sudden, it's jumping around the room like an insect or something. I noticed on a few submitted homework assignments, people were doing p-white and providing integers for the minimum and maximum. Now, this is, there's nothing objectively wrong with this, but it's important to remember that when in SuperCollider, when you make a random selection from within a range, either using a pattern or a unit generator that generates randomness or a language side generator, when the minimum and maximum are both integers, the result will be an integer. When either or both of these min-max values are floats, then the result will be a float. So if we play this, the only values that might come out of p-white are -1, 0, and +1, which means the sound is only going to be directly in front of us and or directly behind us, with a 2 out of 3 chance it'll be behind us. Yeah. If you turn your head 90 degrees, then your ears are pointing at the speakers or the spaces in the room where this is happening. So that's just something to keep in mind. All you have to do, and here's another cool trick. In the language, you can say, for showing something in the post window, post ln, right? This gives us, 2. It actually posts the 2 and then returns the value. So it's just a way of debugging and seeing what's going on. We can't necessarily do post ln here. What this is going to do, I think it's going to say a p-white in the post window. Nope. What did I do wrong? I missed something here. I somehow pushed a 2 there, I think. I don't know how that got there. Yeah, so all it says is a p-white. And it's not, it's correct. This is a p-white. We're saying post ln is p-white, but that's not what we want. We want to see what these values are. And so the method for that is trace. You can trace any pattern in a playing p-bind, and as you can see, we're only getting integers. But if we just make one of these a floating point value, 1.0, and then we get lovely, floating values. Okay, but I said we were going to make this go in a circle. Any idea how we might do that using existing patterns? How would you go about that? Let's say this was on the homework. Pseg is an option. Yeah, well, you can use, not necessarily. If you're going to write out each value, be super slow, depending on how many values you want. So if we say, here's, we know we could do -1, -0.9, -0.8. Good God, no thanks. You could use an iterative process to generate that, I suppose, or you can use the parenthesis. Remember, you can do if you just say 1.10. This gives you the integers, and so if we say -1, comma -0.9 (1), this will give us the array. Whoa, what is this? I have no idea why it didn't just put 0 there, but it put -2 times 10 to the power of -16. Ah, wow. Well, that's very interesting. Sorry, I think I'm the only person that finds that amusing. But this is obviously 0. So then this is an array, and that's what Pseg needs. And then we can say comma inf. Technically this 1 and this -1 put the sound in the same place, and we don't really want to duplicate that position, so we should just only go until 0.9. That gives us that. So this will go around in a circle. Right? So that's working. We have a limited sort of resolution. We could do this. Right? So now it has more values to sequence through, and each value gets spat out 10 times a second. So what's going to happen is here it'll move slowly around the circle, more slowly, taking its sweet time. We can check the size of this. How many values are in here? Was it like 200? Yeah, 200 values. and it takes 1 second for 10 values to come out. So I think it's, what, 20 seconds? 20 seconds to make one full circle? What's annoying about this is that we don't really have, it'd be nice if we could specify how fast we want to pan around the space here and not have to do weird mental gymnastics with dur and pan. Like if I wanted to go around, once every 7 seconds, what kind of increment do I need here? Well, it's just a headache is what you're dealing with. So that is the limitation of using Pseg here. There's it's a good option. I think it's not the best option, and I want to get into a new pattern here called Pseg. P-S-E-G. Pseg. It is a pattern which does time-based embedding of values. Now, actually all the patterns we've seen so far, P-white, Pseq, Prand, those don't know anything about real time. They just know how to output their next value when they are called upon to do so. Pseg actually it generates values which are based in time. So you can say go from this value to that value over this amount of seconds, and whenever you're called upon to make an event, just find out where you are between point A and point B and spit that value out. Pseg, you can think of Pseg as the envelope, the envgen, the pattern equivalent of envgen, the unit generator. And we can actually look at those side by side for comparison. So Pseg expects at least three things: a pattern that represents a sequence of levels in a breakpoint envelope, a pattern that represents the durations between those levels, and a pattern, or a number that determines the curvature, or how the Pseg interpolates from one point to the next over those durations. So let's just step out of this for a second. And so envgen, as we know, takes an envelope, and if we say env.new, we provide an array of levels. We provide an array representing the durations, so maybe a 0.2 second attack, a 1 second release, and we provide an array for curvatures. Let's say 0 for linear, and then -2 for a little bit of an exponential curve. And then this env, we don't even need envgen. We just really need to look at env. And if we plot this, oops, there it goes. Yeah. So env is a language side object which allows us to create something which represents a breakpoint envelope. This is exactly what Pseg does, except it's the pattern version. So Pseg needs a pattern, a value pattern, which outputs these envelopes. I most often use Pseq for this, because it just gives us an ordered array. And then we need a pattern. We'll use Pseq again for the times between these values. We could say 0.2 and 1, and then a Pseq. We could just do. We could just say the whole thing is linear, or you get it. We could do a. You see how I'm going here. Pseq 0 and -2. And then this is just what we'd plug in for, in this case, amplitude or whatever it is we want to control. So let's come back here to our actual pbind. And to make this go around in a circle, well, we need, basically need a starting point and an ending point. Let's start at -1, and we'll go to +1. Let's start by just doing one full circle. So Pseq, and I said 7 seconds to make one full cycle, so we can just say take 7 seconds to get there. And now this is our curvature, and if we want a nice smooth pan, a nice smooth circular motion, what kind of curve do we want between our -1 to +1? Yeah, linear. Right, that's exactly what we want. That's how these patterns work. You give them a nice straight line from -1 to 1, and they make a nice smooth sweep across the space. So we can just say 0 here. Or we could say pseq 0. And then we close it out. Now let's trace this. And let's bring up the level meters. Oops, that's not what I wanted to do. Level meters. And let's see what happens. Yeah, let's do it again. So yeah, see if you can watch. I'll move this over here so you don't have to point one eye in one direction and one eye in the other direction. So it's going around the left, now it's in the front, and now it's on the right, and now it's behind us, and we're done. The reason it only does one full rotation is because the default number of repeats for pseq is 1. We didn't provide anything, so it used its default of 1, which means this pattern occurs exactly once. It outputs -1, it outputs +1, and then it's done. And when it's done, Pseg says, I've got nothing left to do. So it relays that back to the pbind, which is playing, and says, I've got nothing left. So the event stream stops and we get no more synths. But we could make these infinite. And let's see what happens now. All right, so what's it doing? Yeah, it's switching directions. Now, let's think for a moment about why that might be happening. Sorry? It is. That's not really why it's reversing direction. I mean, they do represent the same position. To understand this, we have to think about how SuperCollider thinks about envelopes. It needs a starting point, first of all. And it doesn't need anything else initially. It just needs to know, where am I starting? I will deal with curve and duration when I get my next value, because I don't know where I'm going. So this pseq first spits out -1. And that's the first value that Pseg uses to generate this pattern-based envelope. Then it says, OK, where am I going? pseq, give me my next value. OK, it's 1. Great. Durs, what's my next value? 7. Curves, what's my next value? 0. It says, great. I'm going to go from my starting point to 1 over 7 seconds linearly. Okay? And then it says, OK, where am I going next? Right? It's inf, so it's going to go, oh, my next value is, hold on, I think I just psyched myself out here. So it's, yes, no, yeah, OK, so let's get our sketchbook out here. I think this might be useful. So we're going to look at our pan value here, right? So these, you have to think about, if we were to trace this, if you were just to say, what are we going to see in the post if we trace this pseq? -1, 1, -1, 1, -1, 1, right? And what are we going to see from this one? We're going to see 7, 7, 7, 7, 7. And for this one, 0, 0, 0, 0, 0. So we're going to have -1, +1, -1, +1. This is going to be 7, 14, 21, and it's all going to be linear. So forgive my terrible wiggly lines, but this is the envelope that Pseg is generating. This is why it reverses course. So we're going to have to tweak our Pseg a little bit. Right? We go from back around the front. Here's the front, right? To the back again. This is clockwise. And then we go from the back to the back counterclockwise, right? Going from positive to negative, counterclockwise, right? Clockwise, counterclockwise. So you see? Okay, so how do we fix this? Sorry? Yeah, make it like a sawtooth wave. So we have to think about that. How would we make a sawtooth wave using an envelope generator? Well, sawtooth wave goes from -1 to 1 over some significant period of time, and then instantaneously goes back to -1. So do something like this, maybe, right? So now it's going to take, it's going to start at -1. It's going to take 7 seconds. This is always 0, so it's always linear. It's going to take 7 seconds to go to 1. Then it's going to take 0 seconds to go back to -1. So instantaneously jump, but of course that's the same position, so that it's not going to move at all. And then it'll take 7 seconds to go here, 0 seconds to go back, 7 seconds to go here, right? So I think, I might have to eat these words, but I think this will actually go around in a circle continuously. So we're going clockwise, and now we're in the back. And now it keeps going around. Following that? Making sense? Right. You just so with Pseg, it becomes a little bit of a brain twister initially, but you just need to think about, okay, I'm going to give Pseg 3 patterns, and we know enough about patterns like pseek, prand, pwhite that we just know that they spit out values according to some algorithm. So we say this first pattern, what's the first value? That's where the envelope starts. That's where the envelope starts, and then that pattern spits out another value and takes the first value from these 2 patterns and uses that information to go from point A to point B. And then the next pattern, the next value from these 3 patterns, go from point B to point C, point C to point D. Right, and so then from that, I think we can sort of get a little bit more creative with this. Let's say, let's make it sort of speed up as it goes around the circle. So start slow, and then sort of shoot around to the back, and then start slow again as it comes around to the front, and then speed up as it goes to the back. How would we do that? Right now we're going linearly. So instead of just going at the same speed, with a constant slope, a constant velocity, we want to do something like this. Right? So that when we, and this is my old drawing, right? So now we have a sawtooth wave. So let's it might be 1 and -1. I have to think about it, but so let's just redraw this here. So we've got this kind of thing. And so this is, we take 7 seconds, right? And then instantaneously go down here, another 7 seconds. And with these straight lines, we make a nice smooth pan around the room, same velocity, but we want to do, and I want a different color. Can I have a different color? There we go. I want to do this. I believe a negative value would do the trick here, because the negative values for curvatures are going to bend the curve this way. It doesn't really matter what curve value we get here because it's instantaneous. Any curve is going to be exactly the same. So let's try, and just to make sure we're really hearing it, we'll do a value like -4 or something. So that's going to be even more extreme, like that. And let's watch and see if we've, you know what, we're tracing it too. I think the trace will definitely give it away, because we should see a bunch of -0.999897 just sort of sitting there close to -1, and then as we get around the room, it'll zip up to +1. No, I think we've done it the wrong way. I think it's supposed to be a positive value. So we're in the back, it quickly shoots around, and then comes back. So this envelope here, my negative values, that's interesting. I thought that would have worked, because no, that's right. The positive values cause the curve to change slowly at first, then quickly. Negative values cause the curve to change quickly at first, and then slowly. So what we want is a positive value, right? Somebody please make sure I'm not going crazy. Okay. Programming is hard. So this, if we just simply change the curvature. Yeah. It's making its way around. And then suddenly zips back around. Let me modify this just a little bit. Let's do this and this. So take a moment and think in your heads, how is this going to pan our sound? I can do this. I just changed this a little. Take a look at this Pseg. So infinite Pseq, just alternating between -1, +1. Duration's always 7, and the curve values alternate between 4 and -4. So can you describe to me the output sound?
Yeah, I think it would be it would go slowly around this way, and then speed up as it gets to the back, and then when it gets to the back, it's going to go the opposite direction. But it's going to start slowly, and then speed up as it gets to the back. Or did I get it wrong?
I think you're almost right. I think it is going to go clockwise and counterclockwise, as you said. So it's going to start clockwise, it's going to go slow then fast. And because the next curve value is negative, then it'll go fast and slow in a counterclockwise way. All right, so speeding up. And then it sort of bounces back. And then slows down as it returns to the back of the room in a counterclockwise fashion. Okay. Lots of other exercises we can do, but primarily I wanted to get Pseg out of the way, because that's a really useful pattern. If you're thinking about something in terms of time, how many seconds it should take for some parameter to go from here to from here, with some interpolation in between, Pseg is the way to go, because it's basically a pattern envelope generator. One other thing, and this is mostly a spatialization focused class, but I do want to just bring your attention to filters, because filters are really, really handy and fun for shaping a sound's spectrum. And there's a couple of filters which are great. There's LPF.AR. This is a low-pass filter, which takes an input signal and a cutoff frequency, and it will pass frequencies below that frequency and roll away high frequencies above that cutoff frequency. And there's HPF for high pass filter, BPF for band pass filter, which takes a center frequency and then a RQ value. RQ is stands for reciprocal quality, and RQ should be a value 1, no greater than 1, and greater than 0. It should be between 0 and 1. 1 is the highest value you can have, and you should never set it equal to 0. And heaven help you if you ever set that value to something negative or some ridiculous value, because most of the filter unit generators in SuperCollider have a recursive algorithm. And if you give it bogus values, it will blow up in your face. In the worst, it's exactly what you're imagining. It's just a nuclear explosion. So for low pass, for the frequency values, whatever the cutoff or center frequency is, stay within 20 to 20,000. Stay within the audible spectrum. And for RQ values, a value of 1 is sort of the broadest band possible. So BPF, let's say, SIG, let's put a center frequency at 1,000. A quality of 1 makes this a very broad band pass filter, so it passes a wide band. 1/2 would narrow the band, 1/4, 1/10. As this value gets closer and closer to 0, the band pass filter's band becomes more and more narrow. You can go pretty small. I've I've gone like 1 over 100, 1 over 200. That's generally okay. Just realize that this is going to remove a lot of spectral energy from the sound. The one I wanted to demonstrate is there's 2 other filters. There's a resonant low-pass filter, RLPF. This is a low-pass filter with a resonance parameter. Let's just draw a quick diagram, shall we? Don't save this. Make this. Here is a. This is hertz, and this is decibels, and here's 0. So a high-pass filter, a regular high-pass filter, is going to have a frequency response, like this, where our cutoff frequency is right around here, where the input is reduced by 3 decibels. Here's our cutoff frequency, and here's our half power point. So anything up here above the cutoff frequency is largely preserved. Anything below is progressively attenuated. A resonant high-pass filter looks like, it's going to have, depending on the quality you give it, it's going to look like kind of like this. Right? So there's actually a boost that goes on at the cutoff frequency. So that's the difference. And the closer the RQ value gets to 0, the greater that boost is going to be. So it's really important to watch out for your amplitude. Let's say sig cutoff frequency. We can say RQ. Or if you prefer to think in terms of quality, you can say 1 over Q. I guess I usually do this. And let's add those arguments here. We'll say center frequency equals 1,000 and RQ equals 0.5. Right? Just it's a fairly broad band. And I've forgotten something. I need a semicolon. Right. All right. So now, do this again. You can hear that there's some high-pass filtering going on. If we set our center frequency back to 20, we get the full spectrum. So 200, not that much different. 1,000, 5,000. So not only is it only the high frequencies, it's actually gotten a lot quieter. Not even sure you can hear that. But if we go back to, say, 2,000 and set our RQ value to 0.1, we get a bit of resonance around 2,000. Here's 1,000. And then just to show that we can exploit patterns here, let's do 500, 1,000, ... 5,000. So we're spitting out synths, and the cutoff frequency jumps from these values, right? 500, 1,000, 1,500, 2,000. We can also get creative with the reciprocal quality so that there's more or less resonance. We can even crank it down a little bit. So we get a very strong sense of resonance. It's always good to keep the meters open because with these low RQ values, you are emphasizing certain frequencies. And if there's energy in the sound at that frequency, then you can start to get into the yellow or the red. So just be mindful of that. Okay, so with the last 5 minutes or so we have, I would like to introduce you to the process of, we already know how to export these multi-channel files, but everyone's going to be working on a composition. That's the big main project for this class. Everyone's going to make an 8-channel composition using the techniques we've done over the semester. So I just want to get you a little bit comfortable, starting to get comfortable with using a very basic DAW use. So let's start with what we know. Just make GUI. And I don't know if I've done rect channels, so I'm going to do that. I think I did, but I'm going to do it here just in case. Equals 6. And we're going to make GUI. And now let's just say record. And we've got some spatialization happening here. We'll just let this run for a little while. And then we'll stop. And stop this. And we'll go hunt down that file, which is, so it should be in our music folder, SuperCollider recordings. Yeah, today at 3:47, that's us. So what you'll do is open it in Audacity, and here it is. You can remember just our first two channels have nothing on them, and then you have 1, 2, 3, 4. And on the left here it says mono, 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 and that's what you want to see. We can just X these out. If you happen to be working at home and your first two your tracks are actually here, 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 and here on these four, these first two will say left and right, and you don't want that because then they will export as stereo files with this panned hard left, and this will be a stereo file with this panned hard right. Irrelevant here because they're empty, we're going to delete them, but just for future reference, if you're working at home on multi-channel stuff, the way I fix this is you click and then shift click to select them both, and you say make stereo track, and then split stereo to mono, and then these become mono, mono, and then they will export correctly. But we actually don't need these, so we're going to delete, delete, and now we just have these 4 mono tracks. And the spatialization is all there, right? This is front left, rear left, because that's how pan AZ works. So we're going to go, I think we don't even have to select anything. We go File, Export, Export Multiple. There's a keyboard shortcut for this, which is Shift Apple L. I'm going to use that. Brings up this window. I'm going to export to, might as well choose, go to the desktop, Field Steel. I'll make a folder called Export, Resonant High Pass Filter, Trombone. Create that, and we're going to choose that folder. So now it's chosen that folder. I'm going to do, a SuperCollider outputs 32-bit files. I'm not going to zoom in because High Sierra doesn't track that on the QuickTime recording, but trust me, right over here on all these files, it says 32-bit float. Logic won't read, Logic is the DAW I'm going to teach with in this class. It doesn't read 32-bit float, so I'm going to export these as AIFF 24-bit PCM. And then I like this third option here, numbering after file name prefix. So the file name prefix is going to be Resonant High Pass Filter _ GBN _ we can just stop it there, I guess. And it's going to put a -0 or -1 -2 -3 -4. So we hit export, and we're going to click through this metadata for now. There's a way to disable that. So then it says successfully exported the following 4 files. Okay, and they've gone where we told it to go, which is over here, over here. Here they are. We can confirm with get info that these are all mono files. So then we open up Logic or whatever DAW you want to use, and make a new project. We're going to make a new empty project. So we're going to make 4 audio tracks. So put 4 here. They don't need an input because we're going to drop files onto these tracks. And because we're dealing with the Motu, remember that we want to use 3, 4, 5, 6, 7, 8, 9, 10. You know, like Logic counts like a human starting at number 1. SuperCollider counts like a computer starting at 0. So we're going to say 3 and have these ascend as, so it's going to be 3, 4, 5, 6 when we check this ascending box. And now we can confirm over here, this says output 3, 4, 5, 6. So these tracks are all ready to go. So all we got to do now is grab these 4, I'll just close all this stuff, 4 files, click and drag, drop them right here. And the default here is use existing tracks. That's what we want to do. And so there's our sound, exactly as it came out of SuperCollider. And now it is these four mono files with the spatialization baked right into them. And so from here, now you're in sort of traditional DAW land, and you can use effects, but I think I won't get into that today because we're already sort of over time. But that's the basic process. You can make additional sets of 4 tracks if you want to put another sound that overlaps here. And I'm assuming all of you have some level of familiarity with DAWs, so don't need to go into too much detail here. Okay, so we will get into octaphonic sound next week.